With experimental probability, we're doing trials of an experiment. So we're running an experiment multiple times, and we measure how many times each event occurs. For example, cards chosen from a deck and then replaced. The following table shows the results. Person drew hearts 5 times, diamonds 9, clubs 7, and spades 5 times. Find the experimental probability of choosing a diamond. Now let's remember that 1 out of every 4 cards in a deck is a diamond, 13 out of 52, or 1 out of 4. So the theoretical probability would be 1/4, or 0.25. But the experimental probability is different. So we find the number of times the event occurs, which would then be probability of diamonds occurs 9 times, and then how many trials were there? Take 9 and then add 5. Take 5 and add 9, 7, and 5. Add those all up and we've got 26, which is in simplest form. If we needed to give a decimal, we would give 0.346 approximately, or approximately 34.6%. So in this experiment, it happened more often than was theoretically probable to draw a diamond. Next one, experimental probability of choosing a card that is not a club. And so a couple ways that we can do this one. So we want not club, which means that the probability is going to be 1 minus the probability of a club. So that would be 1 minus 7/26. That would be 26 minus 7, 19 out of 26 for that one. Theoretically, the probability of not choosing a club would be 75%, and this experimental probability is about 73.1% approximately, so a little less likely than 75%. Last one, geometric probability. We're going to find the probability of choosing a point at random and having that point fall inside the shaded area of this equilateral triangle. So essentially what we want to do is we want to find the probability that a random point in this triangle is shaded. And we're going to ignore the fact that we've got like a little blue outline there for this region here. So we want to find the probability of shaded would be found by finding the shaded area and then dividing it by the total angle of this equilateral triangle. So we know it's going to be pretty likely. I don't know if it's, without doing it, whether it's 70% or 80% or 90% or something like that. But it's going to be high. It's going to be better than 50-50. We can tell just looking at it. So to find the total area of this triangle, I'm going to want to use the area equals 1/2 base height formula. So I know that the base of this triangle is 14. I want to find the height. So we can find the height by dropping down in altitude. That's not very straight, but hopefully you get the point. So we want to find how tall is this triangle. Now with an equilateral triangle, I know that every angle in this big triangle is 60 degrees. So this is 60, and we've got a right triangle. So I can use the law of sines, or I can use basic right triangle trig to find this altitude here. I'm going to use tangent because, actually I'm not, well, yeah, I'm going to use tangent. I know that this altitude is going to break this side into 2 equal pieces. This altitude breaks this angle, since it's an equilateral triangle, in half. So this side right here, short side, is 7. I'm looking for this altitude. And so I know the angle, and I want to find the opposite side, and I know adjacent side. So if we're dealing with opposite and adjacent, we can use the fact that tangent of theta theta 60 degrees equals its opposite over its adjacent in a right triangle. Remember, if this wasn't a right triangle that we're dealing with, you'd have to use law of sines. So, enter these into your calculator, multiply both sides by 7, and we would get that x is approximately 12.1244. So that's how tall this is. Approximately 12.1244 inches. So now we'll use area equals 1/2 base times height to find the area of this big entire triangle. So area then is 1/2 times the base, which is 14, times that height, approximately that. Now if you left, or if you leave this number in your calculator, then multiply it by, talking about this whole answer with lots of decimal places, multiply it by 14, then multiply it by 1/2, then we're going to get that this total area is approximately 84.8705. So that's what our total area is. Now for the shaded area is a trapezoid, and it is, so there's a couple ways that we could do this. We could either find the area of the trapezoid, or we can find the area of this little triangle and then subtract from it. So I'm going to pause here and give this one a little thought and then get back to you. So I think that the fastest way to find the shaded area is going to be to find the area of this small piece here and then take it away from the total area. Now I'll find the shaded area. So this top triangle is going to have a right angle here, 60-degree angle here, because it too is an equilateral triangle. It's 4 inches here, 4 inches here, and so forth. And so finding that top triangle's area, we do it in the same way, doing tangent of 60 degrees. But now it's going to equal the opposite side, this x, over the adjacent side. And that adjacent side is going to be 2, because we'll be half of that full 4. Meaning that take the tangent of 60 degrees on the calculator, times it by 2, and we're going to get approximately 3.4641 for this distance here. So to find the area of that top triangle, we will do 1/2. Why do you disappear? I do not know. 1/2 times the base of that white triangle up top, which is 4, times by 3.4641. It's the area of the top triangle up top. We multiply that out, is approximately 6.9282. And so to find the area of this shaded area, we need to take the whole area, and which is this right here, and subtract the top triangle area. If we do that, we get that top triangle's area is about 77.9423. Then, to find the probability, we need to divide numerator by denominator, and we're going to get approximately 0.9184. When we divide that out, which is about 91.8% probability of a random point falling inside the shaded area. All right, so that was a long one. See you in class.